Hello and welcome to today's live stream. Today we will be talking about a few things that we discussed in the previous live stream where um, we talked about the new project where we walk you through adaptive predictive models. And last live stream we went through the parameters, we went through the code, the project, and what the project entails, and what the goal of each week, and what we hope to achieve at the end of each week, and at the end of the final stage of the project. So I mentioned in the last stream that we would be explaining what parameters are and what we log in terms of um, the agents or the agent, which I've been digging through the code to see why the bug exists, or is it even a bug? So that's what we want to also explore in this stream and this live stream, and then explain what the parameters are so that everyone understands uh, when we talk about each parameter, what do we mean? What do you mean? What do we mean? Give me 1 second. Yeah. What we mean by each parameter. So I have a few notebooks. So there is I have this notebook, multi-agent 30. So 30 is just a number of a number that I use to separate each run from each other run. So that is the current run for our data. So if I go to data and runs, so I have these runs right now, right here. So the first one was just one, and then a few runs through that up to 30. And today we will also do another run, assuming that let me see if we can get this. All right. Okay, so today we will do another run for 31. So 30 is the data that I'll be exploring today. So we have the config, we have the data, and then we have the config right here. So I will just walk you through the config, but before that, this is just telling us which folder we will be looking at, we will end exploring. So each folder increases based on the results. So if we run another training now, we'll maybe update manually to 31 so that the training will save the training will save the results in this folder. But yeah, that will come after this. So let me just walk you through the parameters, what they are. Make sure this is large enough so people can see what's going on here. All right, I think that's large enough. Can I go further? No, it's fine. So extended parameter guide. So this is some Wolfram language code if you're familiar with Wolfram language, and just to pass through the code, sorry, the logs. So this code just passes through um, these logs and then figure out what to do, shows graphs, displays graphs, and then does a few operations. But let's not talk about the code. From language code, we will go to params. Now, so each parameter, I have I have the key for each parameter and the meaning of each parameter. So first of all, let me open this in well, let me open it using, can I open it using another thing? So open data, runs, t multi what agent 30, then logs. Let me open with, is it working? Yep, okay. All right, so this is the CSV. This is the entire thing. I ran this for how many steps? Was it 20K? Yeah, this was trained for 20K steps, and each each one was logged. Each so logging is logged. We do logs every 20 steps. So you can see from this parameter, you set it for uh, so this is time. So the time is just the number or uh, what is time? So time is like if you run an agent and it evolves or it trains throughout the time. So time is tracking how the agent moves through each step, right? So that's what time is, what t is. Now coherent. So these are parameters that are logs. There are quite a number of them, but we'll focus on the most important ones. And this is what the Wolfram language code is for. It filters out um, the most important parameters we want to focus on. So as I mentioned, time is just a stepped index loop counter. It counts every time that the agent trains, and each time the agent improves throughout the run. So as you run through as the agent trains, um, time tells us if the agent has improved this time or has done badly in this. Because we're dealing with a predictive model, we want to know how well it's predicting, right? So that's we need to keep time. Then we have coherence. So I think maybe this should be. I should also include what this is. So maybe let me just write it here. So coherent. I mean, so sorry. CH is coherent. Coherence. So coherent. Then CHR is also coherence, and so that it doesn't confuse. But so that's the parameter. So coherent or C or H hat is the forecast coherence. Forecast is predicted. So if you're predicting for if you're trying to find why predict, and let me just also show you what I mean by that. So let's say we go to the code. We want to find predictor. So predictor just takes in so predict. So it takes in X and Y and then spits out whatever value we have predicted. So X is the current, either you are in the current, like the current time step, and then Y is X2, X1 is the current time step, and X2 is the next time step you want to predict. So I will let me see if I can get this here. Is it here? So previous, sorry, the current and then previous. So there are two things right here. So we have previous X. Previous X is you keep track of the previous, and previous x prev 2 is two steps back, right? So if your current step is 2, then if current step is 5, then you want to start from uh 3, I guess. 3, then predict the next step based on the value of the step 3, right? So that's what prediction really is right here. And we are talking about coherence, forecast coherence. So forecast coherence is just we want to predict, we want to know the value of our this, we want to know. I should not edit this. Okay, this is not good. Let's run this again and find out why. Mm, okay, uh, let's just do this again. All right, so why predict? Why predict? Why, sorry, coherence, focus coherence. So we have a function called homeostat. Homeostat just keeps checking the state of the system, the health state of the system. Is it healthy? Is it in a good state? Is it stable? Is it doing well? So Homestu's predicted next step fit after a proposed delta A. So we have delta A. I can show that right here. Delta, delta A, delta self A. Okay, should be somewhere. Is it this? Yeah, delta. We have delta row A, which takes in beta effective, and then so the state of the system plus uh, maybe the gain at that specific state, and then delta S. So we get the delta A through that. So delta A, we want to use that to using the state of the system currently and check what the state of the system next step um, or what we the coherent of the next step state. So you use delta A because it's the current state of the system to predict what the system will be in the next step. So if you want to know how the next step will be, how the current step will lead to how the next step will be, then you check the coherent hat, the focused coherent, then you will know that the system in a few steps, like say k steps into the future, will have performed well or bad. So once we know that, when the system, so actually not us, we don't know this, the system has to know this to keep track of real focused coherence so that it knows if I make this step right now, how well will I perform in the next k steps into the future? So that's what we'll be looking at. That's what focus coherence will tell us at the end of this. And then actually, so expected predictability. So that's what we expect to know into the future. Then coherence is just realized. So realized coherence is the current coherence in the current now. So how does it feel now when I make predictions based on the sensation that I focus on? So if the current sensation, which is X, and prediction, which is Y predict, so that's what we'll be looking at. We want to know how the system is doing now and what the prediction looks like at the current step. So to just give you a sense of this, so we have X. So X is what we are talking about right here. So we have the current sensation uh, of the system, and then we want to get Y predict. Y predict is right here. So we run a prediction. We take the previous one, which I think previous is just one step behind, and then the two steps, another two steps behind. Then we predict uh, what the Y predict will be. And when you have those two, you get now coherence. Coherence will now be the result of that prediction. Now, so if you want to know how the system is predicting at the current step, you use coherence, realize coherence. And if you want to know how the system will do in k steps into the future, you compare with forecast coherence. And then we have meta layer compressions. So in our system, in this system, the predictive model, um, we use memetics, memes, or if you like, and these are like exchanges of information throughout agents with other agents. But then for for you to or for us to know to really know how the system is really performing or how well the system is doing, we need to because we're working with a large dimension of value, so you can't tell really how well something is unless you compress it into something smaller that you can read and understand. Now we call this value or uh, we call it Z in our system. Now Z is the code, the compressed code that so if a system what's this? I don't know. What, okay, if a system has a compressed let's see. If a system has um, receives some sort of what the state of the environment, which can be in any dimension, it has to compress it into a smaller codes, and then picks the best compressed code out of the smaller code. That's what we're calling Z right here. And that explains the prediction and then the prediction errors. Now, if you have a compressed code, it's in our system, it's just it's a one dimension code, 1D, and this 1D has the prediction of what the system is doing, and then I mean the prediction of the system plus the errors, the prediction error. Now we use that to feed back into the system. We can call it back probe, but that's what we feed into the system, and then the system uses that to learn about better predictions. Now, high minus tidy, then we get low or messy. So prediction just tells us like how tiny how well can we compress. Sorry, compression just tells us how well can we compress, and then these compressions can be fed into the system for the system to also learn from the errors it gets or it finds, the prediction errors that it finds. And then stability, oh, sorry, I should also be doing this now. Compression, it's a lot, but yeah, so let's just keep going. So stability, I will do I have something here? Coherence, we have the graph. This is the one that is buggy. It's not buggy, but it's our main source, our main research question or objective is to figure out why at this point in time the system just breaks specifically for richer environments, and we keep going. it breaks, it goes down, just melt, it hits meltdown or something like that. And at the same time, pi, which is attention gain, goes up, and that's what we want to answer. Like, can we, if we figure out, is it a bug or is it something that the system uh, is doing? Then uh, we can go further in this research. But let's do let's just discuss this. And then stability is how stable the system is. We use Jacobian for our spectral stability proxy for proposed A. So proposed A is the state of the environment, or the dynamics of the environment. So I have a function. Let's find it, plugins. So dynamics is what we call the environment. Think of dynamics as the box, or think of the agent as a fish, and then the box, you put a fish in a box, and then water into that box. Now the dynamics of the box depends on no the dynamics of the water that the fish is in depends on how um, the box looks like. If you tilt the box, then the dynamics of the water changes. Now, what we're talking about as what A, so I think let me go to types and should up there, supposed to be, and then predict dynamics. Okay, so 22 here. So dynamics takes in A. So A is so if you for the first I started with a small dimension for training, but then I moved to GPU training where we used torch tensors and dynamics. So this is controlled by a value that is here. So the dimensions of, or the state of the environment, or the observations, is controlled by these plugs. So one what we can do is, so the what A is here is what we feed into the system when at the beginning of the run. So we at the beginning of the run we have A, whether it's a genome, or it's from the base genome when you do evolution, or whether if it's missing in the base genome, we just get the default value of A. Then we feed that into uh, the dynamics as a tensor, and dynamics is so we have two types of dynamics. Let me just open this. So we have A dynamics. This is the transition state transition, or latent dynamics. Latent is just hidden dynamics. We don't see that, or the system doesn't see that as it's hidden. Then, so this is the square matrix we calculate by using n state. So n is the dynamic dimension of the state. So S is just the state, and then ns by ns, you get the whole the whole view of the box, right? Then that maps to current latent state, which is S. So S is let me not mess up stuff here. So S is the state. So let me see. If you go to states, you will see, okay, types and then state. So state is state. I call it water here. Okay, first of all, I should have mentioned why the so much poetry in this code. So for the reason I'm calling water the state as water, and then the dynamics as the box, and the agent, or um, what we are like training as the fish, is because the code or this project was inspired by a project, a poem I wrote some time back, and let me just open that, and we will do some chat GPT code asking questions, but um, let me find the poem. All right. Hopefully we're not diverting from. All right. So these articles. So okay. Hopefully you can see this what this is. Um, this smaller. All right. So the article is this. So the inspiration comes from this idea that I've been thinking about. So like a naive fish, not that knows not what water is, the other is blinded by the cleverness of the design. Perhaps it is in its very nature to not see beyond the box, yet to escape that which it does not comprehend. It so desires to understand itself, for that could be the only way, like the water with no knowledge of how many it saves. The box can only express to itself the existence of the other. As to the other is just, it's but a fascinating mystery. So this idea of um, referential systems, or how like how a self or a system can express to itself uh, the idea of itself. Like it's a complicated idea. It's and I get that like this poem itself is it's a bit um, confusing when you start to think about the self and then the referential system and then how systems try to understand their code or something like that, or their own self. And by the way, this wasn't even close to like AI systems. It wasn't even an idea about or talking about AI systems, but it kind of reflects on um, such systems, or systems that learn from their own experiences, or from their own code, or from the feeding their code back to itself and then learning from that. So it's the same concept, and we the same idea. I think I should also, because this is we are like talking about these ideas in this live stream. So one other concept that this is the reason why I called it. So the project itself is Loopseed. So Loopseed is it comes from the this idea of strange loops, but by Douglas Hofstadter, and he talks about cyclic systems. And so by cyclic is systems referring to themselves, like self-referential systems. So if you are interested here, you can check out uh, his interesting book called Godel, Bach, and Escher. I think it's somewhere here. So it's a good read. It talks about such systems, intelligent systems, mathematics. Talks about art, music, because the first two, the second, these two, Escher and Bach are just artists. Then this guy Godel is just is a mathematician, and the book is not about them anyways. It's about systems, or how the systems interact with each other or with itself. So that's why we are here. We are talking about this state or these dynamics, how systems like these can be referenced into the system, and how the systems like these can be built using ideas that have been there before, have been explored before. Now, there's just a few things I want to talk about. So, water comes from that idea, and dynamics is just the box, and water is just the thing that, uh, or if you think about the fish in the pond, it's the thing that saves the fish, or the fish has to understand for it to survive, or something like that. And the sensorium is the fish itself. Like, this is what X is, what takes in X, the senses of the fish in water. And we have pi, or pi just represents what the fish pays attention to. Is it paying attention to the dynamics of the system? Is it chaotic, too chaotic? Is the water too chaotic, too much turbulence, or and if it's too much turbulent, then the fish has to adapt and adjust its parameters so that it can fit in this new environment that it has not experienced before. Now we have these parameters. So X is just what it's looking at, the observations of the system of the fish, if you like, and that's what I'm talking about here when I say what the senses, the sense. So this is from the state actually. So we have the state of the water, or the state of the system, and then we feed that. So I was saying the current latent state to the next one before the turn nonlinearity. So if the next one is S next, you perform a turn on the A value, the state, the dynamics of what the dynamics of the box. You feed that, you perform this arithmetic, then to get the next prediction, the next state, how the next state will be. And so to calculate that, you get what A will look like. And I can, go through a few other. So proposed A. So proposed A is just based on what the state is currently, the latent state, and then you propose a new A, and then you get that. So stability is used to measure the proposed A, how stable is the system, and all that. Loss lag triggers Lyapunov style penalties. So Lyapunov is just it's a function for measuring is it reinforcement learning do to penalize systems, Lyapunov function. So it's a function for penalizing systems, and it's an ODE named after this guy. So stability. So I'm using this function to calculate stability of the system, and then the function is a necessary and sufficient condition for stability. You can check it out if you're interested. But I'm using this to measure stability of the system, and then we can also go through H. So this is forecast health. So health, think about a fish, right? So the health of the fish in the next step in the future, we have a few weights right here. So weights is let me just go to back off weights. Is it back off or health? Sorry, health. So health. I have these parameters to guide us, or to use as weight. So I have weights, mostly four weights, and you can change them however you like. If you if you want to understand how the system works, and then so the first weight is zero point 0.7, the second is point 2, point 3, point 0.05, and so we do that through we we take the first you times by coherent. Coherent is I don't know. Is it, this should be sorry, I'm not supposed to change things here. Okay. So this I think this is supposed to be coherent current co no focused coherent. So focused coherence, we're taking the coherent part because it's focused the future, and then compressed code and plus stability deduct energy, then we will know how stable is it. So energy is the factor because we subtract energy because we know if a system uses a lot of energy, then we know that the system is harsh on the system on the or the environment is harsh on the system. So if this value is negative, too negative, then we know it's not healthy. If it's a positive or around zero, we know it's a stable function. It's a healthier. It's the system is healthy. And then we have entropy. Entropy Hz. Hz is the entropy of the meta representation. So by meta representation is because the entire system is built on top of is built through by ideas that these ideas of let me find this guy. Is it okay here? So meta learning. It's another learning about learning to learn. This is it in computer science? So, yeah, where automatic learning algorithms are applied to metadata about machine learning experiments. So it's just learning to learn right here. So this is one of the idea that the system is built in with it in mind, and then so meta representation is so we feed in all this plugin we have to the system. We want to know we want to find the entropy. We want to find the entropy of the meta representation. So you have to consider all the system or on the meta plugins of the system to get the entropy. So normalize the entropy of recent Z. So recent Z, we talked about these as compressed code. So Z is what is compressed. What the uh, let me just go to this and show what I mean by compressed code. So the compression algorithm just takes in residual and then the U, and yeah, so it's a lot of information. I think this will take so much time to explain, but we get Z from compressed code. What is returned here is what we're calling Z, and it's a two dimension, maybe U to do two dimension. And then we take that is so normalize entropy of recent Z, what is compressed, then we get the entropy of that system. So I even have these diverse codes. So Hive diverse codes. Code by diversity, so the code is like considering every other things in the system within itself and within the environment. And then if it's low, then it collapses. Let's see how HZ looks like in the system. I don't think I have HZ here. Let me see Z. Yes, looks like it's just zero. Something. something might be, it's not active. What is Z? Do I have C? Z is the compressed. So Z is just compression. I think I already have it in this. Yeah. Yeah, I don't know why this just zero. But yeah, so that's entropy, entropy of the system. If it's low, it collapsed or something. Now, step norm, uh, Frobenius, norm of the safe delta. So there are safe delta, there's safe delta, and then there is just delta, raw delta. Safe is just you clip it or clamp it, then you know it's a safe delta. That's what we're doing in the system. We clamp the raw delta to using a margin or maximum minimum. Then if it's too big, large plastic move, and Frobius. So Frobius is another no, function, normalization function to use, not the guy himself, but Frobius method, um, named after this guy. So this method is to seek a power series solution of a form. So we're using this to do uh, to get a safe step norm, using delta safe. Then energy is just the cost of the current A update. So A, we know what A is. Now, if energy of the current update on A costs a lot of energy, then we can see that through this value of energy, ng. Homeostat energy of delta A. Delta A, that's on the beginning, towards on the beginning of the system. So if you go into the kernel, we'll see delta, no, row A, somewhere. Okay, delta compressed. We got Z compression. Delta is I will homeostat ni homeo. Go to homeo. Yeah, so here we are taking our this is oh sorry, so this is when you turn when freeze I'll talk about freeze um has frozen or freeze step is greater than 0, then we just turn this off, and forecast we just turn it off basically. But if it's desperate, that means that we want to keep going or something like that, then we use a like direct forecast of that safe delta, which I think we're getting just from the raw delta. And so project safe a major like let me start health projected safe a major. So this computes the projection plus, so the if it's improving, then we return that. If not, then we just turn it off, and we get safe as 0. But so energy is just, you have to just keep energy within its so this idea of energy comes from this idea of free energy principle. So if you're familiar with the one of the what one of theories of consciousness, free energy principle is another famous one that is being explored, and it's just a mathematical principle of information physics or the physics of information, and it's in cognitive neuroscience, and like free energy minimization as self-organization, has been proposed as a hallmark of self-organizing system when cast as a random deterministic system or dynamic systems. Sorry. So randomness is a factor in dynamical systems. So dynamical systems need are like if you want to study uh, dynamical system, you must encounter such things as randomness in the system, and so this is because under ergodic assumptions, the long-term average of surprise is entropy. Now we have seen that entropy is a factor we are exploring with our system, which is HZ of meta representation. And this bound resists a natural tendency to disorder of sort associated with the second law of thermodynamics. I don't understand second law of thermodynamics, but if I don't know if yeah, so I think I will have to do that, and then free Bayesian inference. So free energy principle is an idea we can also explore. We are exploring because I'm using energy with a budget. So I have to always keep energy below budget. And we can see this from if we compare, let me find the relationship document. So this notebook just shows the relationship between, this is for 30, the run 30. So this shows the relationship between energy and the budget. Budget, energy budget is the set point we give the system. So we give a system some form of energy budget, tell it, you have to be within this budget. Don't overspend. Don't uh, underspend. You can underspend, right? But underspend only if it's necessary to do that. So we give it some value as a budget. You can give it as much energy as you can, but in our system we do have a way to keep diagnosing the system and see if it's overshooting the energy or it's within that. So for example, here we have seen that it shoots like it spends so much energy at these steps, and I'm guessing it has something to do with our bag, but why it spends so much energy, it shoots so much energy, and then the system now adjusts once it overshoots. The system adjusts so that it doesn't break the system. So because when you don't, it's like you have some energy or you have lost some energy. The ideal way to regain some energy is to relax, right? To go sleep or do whatever you can to get more energy. So to do that, we have a way. We use autopilot. So autopilot just does an update to the budget. I think we need a better name for autopilot. Autopilot sounds like the system is running on autopilot and not doing anything, not planning or doing good stuff. But yes, so autopilot does make some adjustment to energy, does some diagnostic. Is it under is it over, or so we have over something, overshoot or something. I think overshoot. Okay, it should be somewhere in another file. Is it MetaTuner? MetaTuner is just tuning the hyperparameters. So the idea is, you have energy budget. The system has to keep energy within that budget as efficiently as possible so that it doesn't break the system. Because once you don't have energy, the system just, it does nothing. There's no energy to spend, and that's why we do when it shoots, we adjust the budget in real time. And we can see right here the comparison that around these steps it had been under it had been spending energy well. And that's weird because this is the step that coherence, this is like uh from right here to right here, it looks like that's where coherent is not performing really well. And you can see if you compare these, you can see around this step, which is it 840. Actually, no. But yes, it's spending energy well. It's not going crazy on energy. Uh, anyway, so that's one way to okay, so budget, energy budget, delta, and pi is another interesting one because it measures precision and attention, and we saw that from the code in dynamics. So in the sensorium is the senses of like think think fish and what the senses of the fish are, and X is just the current. Wait, let me see. What is X? X. This can guide you. So if you, so this comes into play. So we have state, we have dynamics, we have sensorium, and like from the poem, water, box, fish are memetics. Oh, sorry, meme is memetics. The idea of memes, and the idea of memes comes from this concept of if you've read Richard Dawkins, I don't know how to write this name, but yeah, Richard Dawkins or Richards. Uh, I think this biologist. Okay, so yeah, his book on memes, the book that gave birth to what we call now memes. I I don't know. I forgot the name of the book. Was it the meme machine? Let me find it somewhere here. That's weird. I forgot the name. The oh man, Gene what? Something Gene. Uh, let's see. Selfish. Oh, the selfish gene. So his book, The Selfish Gene, um, gave birth to the idea of memes. Now, what we are more interested in is this one called The Meme Machine by Susan. Uh, so this is a very interesting book where he explores. So we talk about memetics in our book, in our code. We introduce this idea of memetics, and to be explicit, these ideas are just for research. We are trying to explore them to understand if they fit in any way. We are not claiming that we have a framework for understanding consciousness or building a conscious machine or whatever. What we are doing is just exploring these ideas and see what we can, understand or come up with. But this idea of memes comes from here. And then we have memetics, meme layers, and a few other plugs we can, to help us use the system or in the system. Now we were looking for X. So precision update is done by, this update precision takes in coherent energy. So this is stability accumulation. So what is accumulated at that specific step? Then delta H. Okay, so X is what we are interested in. Okay, it should be in our system. So X is this, the senses. So X is the sense. So we pass that to the sense. Sense is the system's current senses or what it's looking at or what it's focusing on. So precision, um, pi. Uh, okay, we were talking about pi sense. Oh, sorry. I think I lost something here. Okay, this. So we were talking about this, the sense of the system, and then what it's focusing on, what is looking at, what the fish is looking at. And then pi is what it's, oh, sorry, how it's focusing on. Like how much attention it's putting on that thing that it's focusing on. So how much attention it's putting on X, if you like. So pi is that just precision, attention, and then so this one is scalar gain on prediction errors. So how much are the errors? How much is gained? So okay, to make it simpler, to make it more simple. So if you look at prediction errors, the system gets prediction errors back into it through compression, right? Compresses the data or whatever it receives, and then it does some sort of um, like focusing on those prediction errors, and then feeds it back to. So this pi measures how much it focuses on prediction errors. If it's too high, if it's high, then it's attentive, volatile or attentive. If it's low, it's relaxed, or call it robust. So one way to understand these is through chaos, introducing chaos into the system. But in our case, we don't actually introduce chaos in the system. We let the system diagnose itself so that it knows whether it's chaotic or like comparison. But let me see if I can get chaos somewhere. Where is let's see. So chaos, I'll just copy these. No, I don't need to overlay it. I need to be separate. Chaos has to be somewhere. Okay. All right. Where is it? Is it? No. Search for chaos. Okay. It's not plotted. Where else should be plotted under this? I'm too lazy to do this. Okay. So chaos is here. All right. So here, this is chaos. And we want to compare pi at chaos. And pi is pi, where is it? Pi is this, hopefully, and chaos is this. Can Can I add chaos here? Maybe I should add chaos. In this data, we have these. Let me add. And then the plot should also include chaos. Well, let me just do this and conceive. So chaos is right here, and we can see that below, just right before chaos goes into the maximum or the ceiling and sticks there. That's the bug. Attention is, high and it's flickering too much. High, low, high, low, high, low. So it's right here, right there, up there. So what this tells us is the system is trying to pay a lot of, like, there's so much prediction errors from this space. So it's paying so much attention to prediction error, and that makes it, like it wants to do better by focusing on prediction errors more, so that it can, um, it can make adjustment to improve itself. So prediction errors go up when chaos kick in. So chaos tells us how much, like, it's more. It seems obvious that we expect when chaos is too high, systems tend to pay a lot of attention to, to it's like survival, something like that. But sometimes other systems can decide to relax. Chaos is there's too much chaos now. I don't want to pay attention anymore. Let me just relax. And that's why we have that's why we have that's why we are saying here that when it's too low, the system, it tells us it has relaxed. It's not doing anything to pay attention to. There's nothing to pay. There's a lot to pay attention to, but it's relaxed. Or there is nothing to pay attention to, so it just relaxed. So it can pay attention when there is chaos, or it can relax when there is chaos. So it's not, they're not too intertwined. It's the system has to decide whether it should pay more attention to chaos or not. Now, attention might be guiding us in terms of how much we should be spending energy on, what we should be paying attention to, and um, all that concept, all that ideas for for prediction errors. And that's about pi, just tension gain, and yes, and then scalar metacode. So metacode, um, meta because it's getting data from the system and from the environment, and then compresses that, and so that code is what the system uses to make other predictions. So we do prediction, and then it turns prediction, and then prediction plus prediction errors, and norm of effective dynamics. So this gets A and then normalizes to get an effective dynamics, and that's just so A prior, and so A prior plus and A prior and plus A, very large ones of instability. So this will guide us. Let's just see that anyways. So it will guide us on what uh, instability. So if you want to know if a system is stable, let's see, where is it? should be somewhere. Okay. Okay. Well, let me see here. Effective. No. There you are. So comparing these, I think I'll just do this. Effective noun. I'll add this to here and effective noun. Oh, stability. So it guides us on stability. And all right, so which one was it? Was it this? No, I need to add. Let me get rid of chaos. Or not chaos, like your drive. Okay. So this, so we have this and this. So around this step, it's 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 not too bad. And then here it's just, um so much going on, so many mountains up and down. So I think since it guides us on how the system is stable, unstable, if it's too high, too large values one of instability, and we can see here um, gets higher, gets higher, and then but here it's a bit lower. This is unstable. That's strange because comparing chaos, so chaos doesn't really affect instability, because if it did, then we should see if chaos is too much here. If chaos is low right here, we expect this to warn us that system is unstable or will be unstable. Should be high, should be low, because there's nothing to warn about. So chaos doesn't really affect instability. And all right, so that's one other factor, and then these are just these are not quite important, but this is sensitivity of the fast output channel to the latent state. So that's not okay. So I talked about these, the of penalties, and then C. So C is the observations, the actual term metrics. So let me show you what C is, where C is. So C should be in dynamics. So we have dynamics here, readout, or what the observation is, and we use nx and ns. This is the state, and then this is what the sense is, what the sense is. Let me see in it. Okay. So I have these two. So this is from C, C dynamics. So this is the state. So this comes from the configuration. So the dynamics, so the dimension, so the state dimension, which is here. So if you look at the dimensions, and this can change. This mostly depends on how much power your computer is, GPU. If you're running on a GPU, then you can go as high as maybe as high as 496, or even larger if you you have a lot of compute power. But um, GPUs are I'm testing this. I just need to go at a smaller value, and observation is just what is observed, and this is just in dimension. So if you do what is observed plus times the state, what is uh, the state of that dynamics, then you get if I'm using this, I'll get 256, get 32,766. That's the how much you will be your your system will you'll be playing around. That so that projects latent state as into the observed actuated channels using these arithmetic. Then you get x from the state and the observation. So each row is channel sensitivity profile over latent dimensions. Large row norm means the channel is highly sensitive, and imbalance can make some sensors dominate the residuals and precision loop. C also defines how assimilation, C transpose at dot product and feeds errors back into the state update. So its geometry shapes both sensitive sensing and so what we can conclude, yeah, what we can conclude is also let me just pass through these hyperparameters. So hyperparameters are just parameters that helps your system to adapt. Uh, Energy budget is one of it, and then coherent target. And I'll show you the coherence target plus in overlay that with coherent. Which where is it? So is it here? Is it other scales? Okay, I don't think I had it. Okay, so this is compression, stability, and energy. This is I can use one of these to coherent and overlay that with the coherent target, and then that will tell us, oh, wait a minute, this should be coherent target. All right, so overlay this. Okay, so I ignore this description because I think this relates to surprise. And so this is the target. This is where we want to always be, right? And it looks like at the first few steps up to 3,080. At those few steps, we are, doing great. We are in the same in the budget. We are in the target. But then after this step, after that, after we hit, what's this step? 31, 3140. Hopefully you can see this. Okay, too much. So 3140, something happens, nothing is happening as it should be. So coherence drops. It just plays around 80. Is it 80? Point 0.8, 0.88 and 0. And from the data, you can also see that. Let me just go and pin this. It does well up to, what was it, 3,000? 3,000, yes, here. then it's something happened around this step. Now that's what we want to find out, what happened around this step where coherence just drops. Now we have a lot of parameters. That's the goal of today, to understand what the parameters are. Then we can figure out which parameter affected coherent or coherent drop. Now it starts playing around 0.8, 0.80, 0.86, 0.881, 886, 886, 8811, 1.173. Yeah, something is happening definitely, and we don't know what that is, so we want to find out. So that's target and the actual value we get, and then so those are what we're calling here hyperparameters, because they tell us how the system is performing. Freeze is a number of steps remaining in which plasticity of A is um, frozen. So plasticity is just how plastic the A is, the dynamics of A is, and then value of information. This is just more of a memetics or memes. So memes is measured based on. So if I'm an agent, and if you run three agents or two agents together, you will measure the value of information of meme exchanges. So every agent may. So what the agents exchange is really just the compressed. We talked about compressed Z. So this is what the compressed code is, what the agents exchange between each other. Now, the value of information is measured based on novelty of the code, and the novelty is just how high is it, and um, um, what so value of information is just delta coherence divided by energy, delta energy, and that's how much the other so agents exchange between each other. So I will show. I think we have. Let me just quickly. How much time? Memetics. I have pool, and I have input and output. Input is how much is coming in to the agent, so how much the agent receives, and output is how much memes the agent outputs or gives out to other agents, exchanges with other agents. So I have this value, and these are controlled based on, like, I have a k. K is just, if you want to slice and pick, you sort how much sort if you receive a bunch of input as uh, better code from other agents, then what you do is you use K to slice the best of them. You sort them first, and then you slice based on you slice K, you get the value of information. And that K is how much you would be using as a guide, or as a value of information you receive to change your code or to do whatever you want to do. And that's controlled by this kappa. So it's a value of information weight for memetics, how strongly value of information is. You can think about how memes work in the current world anyway. So if a meme has an effect to a person, or changes a person's idea, then it's much valuable than a meme that doesn't change. And you can use the same concept as in the cultural way. So, but in this case, we don't use literal memes, but we use code. and code is just the compression of what you receive. So an agent will compress its code. Then from that compression, you pass it to another agent, and it uses that compressed version of the code. But it has to have value, right? If it doesn't have value, if it doesn't affect me in any way, then I will not use that compressed version of the code. Now that's what we want. We also want to explore. It's called meme selection, and we will be exploring this idea as well. And freeze better. This is plasticity, effective plasticity rate. How much plastic is it? Best better scaled by pi scale and further gated by mimetic pool and energy pressure. So plasticity just it's controlled by these factors. And then I think all these are the ones we can leave it. And the data, and then the plots. So the plot tells the whole story. If you zoom in, because you zoom in how and see exactly what's happening. For example, health, it drops a lot of the time. And at this point where we want to really find out what happened, health kind of, drops and then just keeps going. That's not good. And we want to find out. And then energy, we also talked about energy. This is entropy. Now we want to figure out why entropy is always zero as well. So yeah, we might also do some reading about what entropy how entropy aff affects. But this is is entropy information theory. Entropy. Okay. Yeah, so entropy in information theory, this should also be a good way to study what entropy is. Information theory is useful to calculate the smallest amount of information required to convey a message. That's what we're doing, like compression. We're doing some sort of compression, data compression. We also need to figure out the best algorithm for compression. Anyway, so Bosman what? H theorem, what? Bosman H theorem shall not define the entropy H Greek. No. Discrete random. And throughout this, we will be using AI as well. So ChatGPT or whatever to do some research as well. So that will be an interesting one because we need to figure out how to build an adaptive predictive coding model, and maybe how to actually test it. Does it work? And one of the environments we want to be testing this on is cellular automata. So cellular automata, for those who are familiar with it, will be our testing ground for um, cellular. I can't type. What is going on? Okay, so cellular automata, and specifically, we want to be looking at neural cellular automata. Um, this is yes. So this is a nice section to play around with these guys. Like it grows itself when you delete it. It's sort of memory kind of concept. Like it tests how memory can be encoded in a s- in a cellular automata kind of way. And yeah, so that's one way we will be one thing we'll be testing these on. Hopefully hope I'm not saying it will work, and I'm not saying that it's something that is the right way to do it. What we're just doing is experimenting and trying out things to find out if it works. So the next session will be, let me just make sure we have all the parameters discussed. And let's see, where is it? No, this. So we've talked about all this. So if you see coherence, think about realize coherent, what the current coherent, and then relationships. So relationships is also it's also here. We can also go through the relationship and we can, relate them how they work. What I haven't talked about is energy against coherence. So we have energy. We can do energy against pi. No, sorry, coherent against pi. Okay, should coherent against pi, and you'll see this. So around this, so coherent is playing around 1, 8, and 0. So it's around 1 and 8, and just there's just one that's weird. 20 steps, and we have just one that is within this guy, within this 2.17. So 0.17 is just one, and all the time coherent has been either 1 or zero point 0.8 or zero point 0. And so as pi increases, so it's just playing around this area, and that we will do comparison along the way. We'll run experiments, and we will do some live coding too, using using also AI to also guide us. So AI also, we will do some analysis using ChatGPT. So we will, for example, if we run a system and then generate code or generate data. So data is this. So we will be having data on this. If it's an agent, if it's multiple agent. If it's multiple agent, we will see something like this. Let me see. So if I open this was run by for three agents. So agent 0, agent 1, agent 2. And if you run more agents, it will still show right here. So um, that's what we'll be doing. And tomorrow I think we have a session we can do tomorrow, I think. Yeah, maybe. Okay, so and there are other things, plugins that I haven't really talked about. And richer actor is just, richer actor, self-explanatory. It's an actor in an environment called richer. And regime, registry, sensorium, spectral guard, state, TNS. Yeah, so we will explore this. And fun thing is we'll be using uh, Mathematica to do analysis. And yeah, I think that's it. That's it from my side. I don't know if there are any questions. Let's see. Any charts? No charts. Awesome. All right. Looks like we have no charts, no nothing. to address. So thank you guys for watching, and thank you for staying with me for an hour and a half, and see you next time, the next stream. Thanks. Bye. Uh, all right.